Hello, good morning, everyone. Yeah, thanks all for coming. And then let's start the class today. So it will be a very simple class. So starting from this week, we will be talking about a lot of graph algorithms. So, so today we will first talk about some representation of a graph, and then we will specifically mention one of the famous and useful algorithm called breadth search. So the nickname or the shortened name of breadth search is BFS. So yeah, you will see or you will hear BFS all the time. So what is a graph? Let's review. So a graph consists of a set of vertices. So here there are vertices. And then there are also edges joining vertices. So here in this graph here, we will see that there are 5 vertices with labels 1, 2, 3, 4, 5. And then there are 1, 2, 3, 4, 5. There are going to be 6 edges on the left-hand side. And then for the edges, so you can imagine that edges represents connection between the vertices. So in some case, the edge does not have any direction, but in some other case, let's say it may be representing some roads between the cities, so the edges could be directed. So in the graph on the right-hand side, all the edges are directed, and then we call this a directed graph. And the left-hand side, it is an undirected graph. So here, this is a special case. So this is an edge that is pointing back from a vertex to itself, and we call this a loop. So how do we represent a graph? So let's take this left-hand side graph as an example. So one way is we specifically maintain a list for each vertex so that it tells us what are the neighbors of the vertices of this vertex. So what are the neighbors, what are the vertices that is joined with an edge to this vertex. So if you look at this example, vertex 1, it has neighbor 2 and neighbor 5. So there is a list pointing to 2 and then 2 points to 5. So this is a linked list of the neighbors. 2 has neighbor 1 and 3. So 2 points to 1 and 3. So there is no particular ordering between the vertices in this list. So like this, vertex 3, its neighbors are 2, 5, and 4. So we have 2, 5, 4, and so on and so forth. So this is one way to represent a graph. So with the information here, we can easily construct the graph back to this drawing. This is called the adjacency list because adjacency means they are neighbors of each other. Okay, now this is another example. This time we have a directed graph. So if you focus on the vertex 1, although there is an edge pointing from 2 to 1, then we don't call 2 as a neighbor of 1 because 1 cannot reach 2 in one step. So 1 will have just one neighbor, direct neighbor 5, and then 2 will have neighbor 1 and 3, 3 will have neighbor 2 only, 4 will have 4 itself as its neighbor, and then 5 has 2 neighbors. Okay? Okay, the good thing here is, okay, so let's analyze a little bit about the adjacency list representation. So suppose that the graph G has V and E as the vertex set and the edge set. So the total space to represent an adjacency list is the size of V plus the size of E. Reason, if you look at this, so there are 1, 2, 3, 4, 5. So there are 5 lists here. It is because we have 5 vertices. And then for each vertex, we will point to the corresponding neighbor. So each time we point to a neighbor, it represents a particular edge. So for the directed graph, the total number of pointers here, 1, 2, 3, 4, 5, 6, 7, it represents each pointer corresponds to a certain edge. And then for this one, you have more pointers, but then you will see that there is a pointer from 1 to 2, and there is a pointer from 2 to 1. It is due to this edge joining 1 to 2. So we can see that each edge here actually has 2 copies on the right-hand side. It is represented by if there is a vertex U and a vertex V joining by an edge, you will see V in U's list and U in V's list. So that's why the total space here is still bounded by 2 times the number of edges. Okay, and then this adjacent list representation is very good when the space in space when the number of edges is only a few. We will see a different type of representation soon, and then for that representation, it is not good when the number of edges is small. And then using this representation, it is easy to find out all the neighbors of a certain vertex because we just need to traverse the corresponding list. And then, but then, but then on the other hand, this is something that is not good. If I just want to check whether a certain vertex 1, let's say, is connected to 7 directly, then maybe we will need to look through all the neighbors of 1 before we can confirm whether the vertex 7 is a neighbor or not. So in that case, in the worst case, it may take order v time to check if a certain vertex is a neighbor of another vertex. And the representation can easily be generalized to represent a weighted graph. So what is a weighted graph? This is something like we may have weight on the edges. So here, this is just an arrow, but then we may associate this with a certain value representing the distance between the two cities. Or we may associate a weight for a vertex representing some cost or some benefit if we are choosing this vertex. So in the stinky tofu shop homework, so we will have some associated benefit, number of customers that you can bring in if we open a stinky tofu shop at a certain place. So in that case, we are going to associate a certain value to each vertex. Okay, so this is the adjacency list representation. And then there is another one called adjacency matrix. So what does that mean? So we are going to use a V by V size matrix, let's call it A, to represent whether two vertices they are adjacent or not, whether they are neighbors or not. So in this example, so here 1, 2, 3, 4, 5 represents the vertices, and then this is also the vertices. So 1 is joining to 2 and also 5. So in that case, we will specify this by 1, 2, this entry, we'll put a 1 there to represent that 1 and 2 are neighbors. And then 1, 5, in this particular entry, we will also specify this to be 1. All the remaining entries in this row, they are 0 because 1 is not a neighbor of 1, 1 is not a neighbor of 3, and 1 is not a neighbor of 4. So this is a very easy to understand representation. So this is for this graph. We can check carefully one by one, and then it corresponds to something on the left-hand side. And similarly, we can use this representation for a directed graph. So like this example, so 1 has an arrow pointing to 5. So 5 is a neighbor of 1. So 1 can reach 5. So 1 can reach 5, so we put a 1 here. But 1 cannot reach the other vertices directly, so we put a 0 here. On the other hand, 2 can reach 1, so we can see this 2 can reach 1, and 2 can also reach 3, so 2 can reach 3. And then for this vertex 4, 4 can only reach 4 itself, but no other vertices. So basically, we used 0 to represent there is no direct connection, and 1 to represent there is a direct connection. Okay, so this time let's analyze the performance of using an adjacency matrix. So no matter how many edges are there in this graph, the adjacency matrix representation always will use space order of v square. So because there are going to be v square entries here. Okay, but then we can be a little bit more careful. If we just want to store 0 or 1, then this order v square, you can say it is order v square bits. Okay, so because we just need a 0 or 1 bit to represent each entry. So the space could be made a little bit smaller. But we will see that this representation could be bad. Let's say when you just have very few edges, and then in that case, by storing these few edges, we are using a so big matrix to represent it. So it is not a good way if we are concerned about the space. But the benefit here is we can do something much faster than the adjacency list representation. This time, if we want to check whether a certain vertex is connected to another vertex, we can use random access. It takes constant time to do so. But on the other hand, another bad thing here is if we now just focus on listing all the neighbors of a certain vertex, then because we don't know where the locations of ones, we don't know. So we need to visit through. So let's say I want to know what are the neighbors of one. I need to check this entry, this entry, this entry, this entry, this entry before I can tell for sure that how many neighbors are there for one, and then what are they. So in that case, it takes a long time when it is compared with the adjacency list representation. But the matrix form is also flexible enough to represent a weighted graph. In that case, if I want to have weight on the edges, then that's easy. I can simply write down the weights here. But if there is no edge between two vertices, then it depends on what we are looking for. If it is representing a distance, then in that case, 1 and 3 is not joined by an edge, then perhaps we are going to write an infinity symbol here to represent that they are not connected. And then again, we can also represent weight on the vertices by storing the weight associated to the vertices separately. So this can easily be adapted for storing a weighted graph. Okay, now this is just some side note. Okay, so we define what is meant by a transpose of a matrix. So let's say A is an n by n matrix. The transpose of A, the notation is A to the power t, so t stands for transpose, is an n by n matrix. So you see the n by m changes to n by n. So it is like a flipping operation such that the entry in the transpose UV is the same as the entry of VU in the original matrix. Now, so if a graph is undirected, then we will see that if there is an edge between V and U, there will be an edge between U and V. This happens if and only if. Okay, so in that case, A and AT will be the same. Or equivalently, if you look at this, this is a adjacency matrix of an undirected graph. So what does that mean? It means that the matrix itself is symmetric along this diagonal. So it is like flipping operation. If we have one here, there is a one here, a zero here, a zero here, a zero here, a zero here, a one here, a one here. So it is like a mirror image, and then it is symmetric along this diagonal. Okay, now we are ready, okay, to talk about algorithm. So the first graph algorithm that we want to introduce is called the Bfs algorithm, breadth search. And then this algorithm is very simple, and then the target of this algorithm is given a particular vertex S as the source vertex, we want to find out all the vertices that are reachable from this source. So imagine that this represents rows, and then this represents cities. So if I start from a certain vertex 3, let's say, what are the vertices that I can go? So for instance, in this example, if I start from vertex 4, then I can go to nowhere except the vertex 4 itself. So this is the the target of the problem that we want to solve, and then BFS is one of the algorithms for solving this problem. So today we will talk about BFS, and then next week we will talk about another algorithm that does the same thing. But then it uses on a different strategy. So what is breadth first search? Breadth means the width. Yeah. So we go, okay, so this idea here is that we are going from S at the beginning, and then we will try to explore the vertices of the graph in rounds, such that at round K, we will visit exactly all the vertices whose distance from S is equal to k minus 1. Okay, so round 1, we will go to visit all the vertices with shortest distance from S is 0. That means that at round 1, we will visit the vertex S itself, and that at the next round, round 2, we'll go to find all the vertices such that it is exactly one step away from S. And then after that, in the next round, we will find out all the vertices that is exactly 2 steps away from S, and so on and so forth. So the algorithm will stop until we do not find new vertices. So if we write it in a pseudo code form, so this is what we are doing. So we first mark S as discovered. So we are going to discover this at round 0. Okay, yeah, the round number may be a little bit is shifted, but that's okay. But the idea is like this. So at the beginning, we mark S as discovered, and then for the subsequent round 1, round 2, round 3, and so on and so forth, we look at any vertex that is discovered in the previous round. And then we are going to visit the vertex. So once we mark S, and then we will discover it, and then we will visit it. And what is the purpose of doing this visiting? So by visiting the corresponding vertex, we will be able to see more information about this graph. So at this moment, once a particular vertex is visited, we will try to look at all the neighbors of U. And then if a neighbor is not visited or not discovered before, so actually not visited and not discovered, we can simplify this as not discovered. So if a certain vertex is not discovered already, then we will mark the vertex as discovered, so that in the subsequent round, we will be visiting this vertex. And then here, this loop, we can see that will stop whenever there is no new vertex discovered in the previous round. So that means that all the vertices has been discovered, and then it is already on the list. Okay, and then, okay, let's see. So let's see how this algorithm runs. Okay, so suppose that we are beginning with S, and then the dotted line represents discovered. So we discover S here, but then we do not visit it at this moment. But next time, we really visit it. Okay, when we visit it, then we will mark down the distance of this vertex from the source. So we mark it as 0. Now when I have 0 here, then I now really visit this vertex, so I can see more. I can see these 3 connecting vertices. So I will add them as the discovered vertices. And then after that, this is the end of round 1. So we are going to do round 2. Round 2 will pick any one of them and do the visiting. And then by visiting this, we try to discover some new vertices, but there's no to discover, so that's okay. So in that case, so we are done with this vertex. And then we are not ending this round yet, because there are still some vertices discovered in the previous round. So there are still these 2 vertices. So what we do here is we continue the process. Let's say we are going to visit this one. And by visiting this one, we see the graph more. So we are going to add this as the discover node, so that we can look at it in the next round. And it's not end yet, because in the current discovered list, we still have 1 vertex. So we visit this one, and then discover this one. Now after that, this is the end of round 2. So we are going to start round 3 now, because at the end of round 2, we have now worked on all the vertices that is discovered in the previous round. So we now go to the next round. So the next round we'll look at this vertex and this vertex, because these are the 2 vertices that are discovered. So we look at this one, and then nothing to add. Good. And then we look at this one, and then we add this one. Is that okay? And then we are done with this round 3. So we are going to go to round 4. Round 4, visit this one, so that we are going to discover this one. Is that okay? So we still have something discovered. Okay. And after that, it's done. Okay. So we'll go to the next round. We'll visit this one, and then we see that there is nothing discovered. So once we find that at a certain round there is nothing discovered, so there is nothing that we need to work on for the next round. So in that case, the algorithm will stop. Easy, right? So there is one thing that I want. Okay. So this capture. So when there is no new node discovered at a certain round, then we stop. Now, if you look at this, so when I process this algorithm, I'm actually marking some arrows here, some edge. I mark it. So when I mark an edge with a directed arrow, it means that it is this node who discovered this node. So that I draw a pointed arrow from S to R, because S discovered R, S discovered W, S discovered X. And then here, when we process W, although W will look at X as its neighbor, but then X is already discovered. So it is not W who discovered X, but X is already discovered by some other node before. So we don't draw an arrow here. And so on and so forth. So in the end, you will see that we will actually get a tree with S as the root, S is the source as a root, so that S points to all the distance 1 neighbor directly, and the distance 1 neighbor points to the distance 2 neighbor that they discovered next, and 2 points to 3, and 3 points to 4. So this is actually a tree structure, a rooted tree structure. This rooted tree is called a BFS tree of S. Now notice that the BFS tree is not unique, so it depends on how you write your algorithm. So you can have different BFS tree obtained by with the same graph by running different algorithms. Okay, now why do we? So it is a simple algorithm, but why is it correct though? So the correctness of this algorithm can be proven easily by using induction. We will see that a vertex V is discovered in round K if and only if the shortest distance from V and from the source is exactly K. So we can prove this easily by induction because, so the key point here is that if a vertex is at exactly K step, shortest distance, exactly K step from S, it must have a neighbor which is exactly K minus 1 step from S. And then if this neighbor is correctly assigned or correctly discovered in a certain round, then the one step more neighbor will be correctly discovered in the next round. So this is the idea of how we can prove this algorithm to be correct. Okay, so here, although we are looking at an algorithm that looks like that we are going to maintain a list of vertices discovered in each round, but then we don't need to do so. Okay, when we implement this algorithm, we just need to keep on a single list that is going to be shared by all the vertices discovered in different rounds. So what we do here is that what we need to do here is that we will talk about this later. So here, this is so we don't need to do a separate list for each round. We can use a common queue. So whenever a vertex is discovered, we will put it at the end of the queue, and so that we always draw the first vertices at the front of the queue to visit. And so we visit the vertex, and then all the neighbors will be put in the end, and then we visit another vertex and put all the neighbors that is undiscovered to the end, and so on and so forth. So by doing so, we are going to visit the vertices according to the rounds that they are discovered in this sequence. So there is no switch round. So we will be operating in exactly the same way as we are using separate list. So we can simplify the implementation by keeping just a queue, a common queue for all the vertices to be discovered. And then for the time analysis, so we will see that this algorithm just need to do what? Just need to do some marking of the vertices and then putting the vertex on the queue and then putting and checking the neighbors of it. So we will see that the total time is actually V plus E, because if you look at this algorithm from the start, each edge is only visited twice, is being checked twice. So the first time is checked, it is when S is being visited, and the second time it is checked, it is when R is visited. Okay, so this edge is only looked twice, and similarly, this edge is only looked twice. The 2 times that we are looking at this edge will be when T is visited. So in that case, we will be looking at all the neighbors of T, and at the second time, or another time will be when we visit X, so that all the X neighbors will be checked. So in that case, the time that is involved in checking the neighbors will be 2 times the size of the edge. And then on the other hand, how about the vertex? So each vertex will be put onto the discovery list only once, and then it is never discovered again. So in that case, the time that is corresponding to the vertex will be V. So in total, this is the total time, V plus E. As for the space, then we will need to keep the adjacency list. So we are using adjacency list as our representation. So the total space is V plus E as well. And then notice that we assume to use adjacency list. If we use adjacency matrix, then the running time is not like this. Okay, so that's all. Yeah, that's the end for this lecture. So if you have time, yeah, try to write a program, yeah, to test your understanding. So usually a BFS algorithm, the program is very, very, very simple. As long as you know how to input a graph in your program, then yeah, represent the graph with adjacency list. Then after that, searching for the working for the BFS is actually a few lines that you can do. Okay, so that's all. So let me check if you have any question. Hey, excuse me, it's not this one. It's not this one. It should be this one. Yeah. Okay, so yeah, if you don't have any question, yeah, so let's end the class today. Yeah, thanks all for coming. And then yeah, if you have questions afterwards, yeah, please leave us message so we have represented. Yeah, thanks a lot. We have got the what? We have got a question form. So there's a link to the question form that you can find in this YouTube live video, or you can send me or the tutor's email directly. Okay, so yeah, thanks again, and then see you next week. Bye bye.